in this problem, we are given a reaction which is actually the first step of glycolysis. And glycolysis is a catabolic pathway that has the purpose of oxidation of glucose all the way to pyruvate, right? And the first step is to phosphorylate glucose using the ATP molecule as a phosphate group donor to form glucose 6-phosphate, and of course, once one of the phosphate group of ATP is transferred to glucose, to the 6th position, to the 6th hydroxyl group, another product is ADP. So we have two questions: to calculate delta G under standard conditions for this reaction and equilibrium constant. We know that delta G for a complex reaction as is, that's actually a coupled reaction, right? So delta G for this reaction can be calculated based on the delta G values, standard free energy change values, for the simple reactions of hydrolysis of phosphorylated compounds. So we have the first reaction, which will be ATP hydrolyzed into ADP and inorganic phosphate. And for this reaction, we know that standard free energy change is minus 30.5 kilojoule per mole, right? And then we have the second reaction, which will be hydrolysis of glucose 6-phosphate into glucose and inorganic phosphate. And the free energy change for this reaction, again, is tabulated. It is equal to minus 13.8 kilojoule per mole. So for this reaction, for the original reaction, delta G can be made of the delta G for ATP hydrolysis. And then for the second reaction, you see here the substrate of the reactant for this reaction is actually the product of our original reaction. That's why we need to flip the reaction. And when we flip the reaction, of course, we switch the sign, right, from minus to plus for delta G under standard conditions. So we'll have minus 13.8. So this resultant standard free energy change will be minus 16.7 kilojoule per mole. And of course, we can calculate the equilibrium constant for this reaction as E of minus delta G naught prime over RT. And when we plug the numbers, it will be plus 16.7 by 10 to the third, because it's kilojoules here, right, over 8.314 by 298. Whenever temperature is not specified, we can use 25 degrees, which is actually the temperature for the standard biochemical conditions. And this value will be equal to 846. So now, what if we want to determine the maximum achievable ratio of glucose 6-phosphate over glucose? And I'll shorten glucose 6-phosphate into G, 6P, and glucose will be just G, right? So I want to determine the maximum achievable ratio between the product of this reaction, glucose 6-phosphate, and reactant glucose, the concentrations. For this reaction to still be spontaneous, because we know that even for such exergonic reaction, if you have too much product, the reaction can be inverted, right? So how can we calculate that? We know that for the reaction to be spontaneous or thermodynamically favored under any given conditions, we can calculate free energy change based on two terms, the standard one and the one that depends on the concentrations, the ratio between the concentrations of the products and reactants. And we are interested for this reaction to still be spontaneous under given conditions, right? So it needs to, the delta G for this reaction needs to be negative. So another thing, we will assume that under these conditions, concentration of ADP equals to that of ADP. So we'll kind of cancel out those. And so now we can calculate the ratio based on that. So RT, oh, sorry, RT logarithm, of course. I'm so sorry. RT logarithm. RT logarithm of the ratio that we are looking for should be less than minus free energy change under standard conditions. If we now divide both parts by RT, and I'll just to save space, I'll do it like that. We know that here this value is actually equal to logarithm of the K equilibrium, right? By definition of the by the way how we relate delta G standard with K equilibrium. So it means that for the reaction to still be spontaneous the maximum ratio of the products over reactants of the glucose 6-phosphate over glucose should be less than the equilibrium constant. Less than equilibrium constant. So as soon as you increase the concentration of the product, such as glucose 6-phosphate, so that the ratio between the concentration of glucose 6-phosphate and glucose exceeds K equilibrium, the reaction will proceed into the opposite direction.